All right, so hey everyone. So this is going to be the second stream of the day. It's going to be another speed run of another really good book called Data Science from Scratch. I really enjoyed this book because it sort of goes over how to do everything from scratch in machine learning, like including a basic linear algebra library, the gradient descent, some code for logistic regression. And for me, at least, it was like the book that I credit with making me get how to write machine learning code outside of a library. It really deepened my understanding a lot more than a lot of the more mathy references did. And once I understood the book, I was able to appreciate and understand the mathy references a lot more. So I hope you'll enjoy it as much as I did. All right, well, where was the book? Yeah, it was here. All right, so this is a book by Joel Gross. And it's just like absolutely fantastic. So I'm just gonna go over it. Like, it's not a short book, but I would say definitely the main ideas are covered early on. And so here, let me just show you. Blah blah blah. Right. So this is like here, for example, what I liked about Joel's book at the time was he has like all sorts of like nice tricks. For example, where like let's say here, things I like about this book is that it has like all sorts of like nice patterns. Like for example, here. Like it uses this pattern, which is like, let's say, for example, taking like this like total number of connections that a user had is like the number of friends per that each user has for user and users. So this would be sort of similar to saying for user and users, total number of friends plus equals to number of friends user. This is just shorter and like more functional and vibe. And it's how I ended up writing a lot of my Python code these days. Like lists are very, very powerful in Python. So a lot of this stuff here, this sort of, I don't know if you remember like my previous video when we talked about like bucketing, like this is sort of what bucketing the code looks like. It's literally just like an if condition, and then like updating some counts based on those conditions. All right, let's see, it's the interesting stuff. A crash course in Python. All right, that's fine. Like there's white space, you have modules, functions, strings. Okay, that's all fine. I don't want to cover this right now. Um, but yeah, like I think one important thing in Python is that like the most fundamental data structure is a list, and then arguably after that it's a dictionary. And what's interesting about these data structures is that you can implement any data structure with these. Like it's not going to be necessarily the most efficient without pointers, but it's definitely like I mean it's one of the reasons like why I really like Python. Let's say for like these like let's say even like things like programming interviews or something where you have to come up with something fast. It just ends up being like much more pleasant as opposed to just resting with the language itself. All right, tuples are also interesting in that like well you can't modify them, and the order doesn't. I believe the order doesn't matter. Like it's sort of like a set. I don't necessarily use tuples all that much. Dictionaries are very very useful. You can basically let's say if you want to represent a graph, like in Python, you could have like a node be the key, and then the value is a list of the neighbors. That's something I really really like about Python. Thank you for the new subscribe, Enrique. I appreciate it. Feel free to ask me any questions. I'm doing a speed run of this book, and I'm happy to answer any questions. So just let me know. Right. So other stuff are useful, like let's say counters, like counting the most common words. Like a lot of these patterns are basically here. I will say just generally this pattern in Python, which is like for let's say word in words do something. Like this is a very common pattern in Python where people will just have like for something, for something, and then this is just generally like more senior Python devs end up writing code, which is hilarious. Stuff like control flow, yeah, sure, you have if conditions, so it's all fine and good. You have Boolean, so it's not necessarily what we're most interested in discussing. So this is a feature about Python I really like, which is list comprehensions. And so list comprehensions are basically a way to compress something that looks like four word in words, do something. You can have this be a one liner. So for example, like let's say you wanted to have all even numbers. You could say, well, I want all numbers x for all numbers x which are in the range of 5. So basically all the numbers from 0 to 5. And if that number is divisible by 2, right? So if modulo 2 is equal to 0, therefore put it in this list. Same for squares, same for even squares. This is very useful. Like one syntax that I particularly like in Python is the dot product between two vectors. So if you're doing the dot product between, let's say, vector v and a vector w, in Python, this would look like for, there's two ways to do it. There's a few ways to do it. There's two good ones. So one could be for vi, wi in zip of vw, and then you say uh, vi plus wi, so total equals this, and then return total. And let's say total equal to 0. So this is still pretty nice relative to other languages, but you could make this even shorter if you say, well, I want you to actually return vi plus, yeah, sorry, so the sum. So I want you to return the sum of, sorry, no, like vi plus wi for vi in v for wi in w, and then do this. Right, so then you end up with a list, right? And then you take this, let's say this is a list equal, then you take sum of list. And so these would be the same, but this is 2 lines of code, whereas like this is 4, right? So you just decide whatever is simpler for you. If you find this syntax confusing, sorry, I need to do a better job splitting this up. So let's see this syntax here. If you find this confusing, then you can just use this. So like for loops, and then list comprehensions. All right, so moving on. Some other really interesting stuff about Python is the idea of generators and iterators. So this comes up in two settings. Like one is when you're working with infinite data, which is like streams. So what does that mean exactly? Like let's say you want to take the range of a list, but then this list doesn't end, or you want to generate all integers, but you don't want to store them all in memory, right? Because there's an infinite number of integers, you're going to run into an out of memory overflow. Instead, what you want to do is just have the user basically ask for the next number, and as long as they keep asking, you're going to give them the next one. And so the difference there is instead of having a return statement, like the only difference is that you have a yield statement, and that's pretty much it. So it's really nice. It's like a nice like syntax trick that make you work over infinite data. And if you've programmed with some JavaScript or done some web stuff, this stuff should be familiar to you because you're working with like events that may have not happened, right? So other stuff like here, so there's another example of list comprehension, right? Let's say I want to generate 4 random numbers. So I'll say for random.random. So that's like the random library called the random function. And then for, this could be for x in range of 4. Here, it's just that we don't care what x is because we're not using it to do anything. But instead, like let's say if this was random.random times x, then you could say something like, well, for x in range 1 to 4, and then that would multiply each random number by 1, 2, 3, and 4 respectively. Other stuff that's very practical is random.choice. So let's say you have a list and you want to like randomly sample from it, then you could do something like random.choice, and you can also say, well, I want to randomly sample 6 times from lottery numbers, for example, where lottery numbers range from 0 to 60, right? So these are very practical helper functions. I use them quite a bit to generate fake data to test models. And the reason you want to do this is often when you're working with any sort of ML model, you want to know if it works, right? Before you just like, let's say, start pre-processing data and downloading it and doing some stuff and loading it, and then it fails, 5 minutes in. So instead of that, what you can do is just give it fake data, validate that the model works on some fake data that you can generate very quickly using random sample, random choice, and a bunch of other helper functions like these. And then you should be good to go. And then if it works, then you can try out real data, and then things should just work. So within Python, the way object orientation typically works is that each class, like set, will have its own function. And so here, for example, like that we're inventing a class for a set, and then, well, what do you need to do with a set? One is, for example, rep is basically a core Python like function for object. So that's where this double underscore comes in, and you basically use this such that like, well, if you create a set and then you say print set, you basically say, well, okay, well, when this gets called with print, I want it to say set and then list out all of the keys of a dictionary as a string. So that's where the str is. So what else do you want to do with the set? Well, you want to add stuff, right? And so, and then another thing is, what you want to wonder, well, how can I know if something already exists, or how can I remove it? And remember when I said all data structures in Python can be implemented with lists and dictionaries? Like, this is a very core thing. And so again, remember like that, if you're trying to build out some sort of data structure, you can do this. And in fact, like most of the interesting work is already being done in this line of code here, right? So this dict essentially lets you bootstrap a whole bunch of other kinds of complicated data structures. So they also talk about like partial function application and some functional ideas here. A map is basically applying a function to every element of a list. A partial is a way to apply a function, basically compose functions without applying them. So let's say you have a function for squared, and then you have a function for adding all the elements. You could have that function and pass it around as a data structure, as a parameter to some other class. But you don't need to actually apply it on some specific data. So this is very practical, especially if you combine it with maps and reduce and filters and stuff like that. Enumerate is one of the most useful Python functions ever. So, typically in like, let's say C code or something, like you'll have like a while loops, and you go like, well, while like sorry, like for I, and then I less than n, I plus plus. And then, but here instead with Python, what you can do is like, while you're iterating over all the elements in the list, you can also create like an index for yourself. Like that's what I is here. And this is a very, very useful feature of Python that I use all the time. Like I always use enumerate. So zip is useful because if you have two lists, what you can do is you can make them a pair. And then once they're pairs, you could apply a for loop on both elements of the pair at once. This is very useful in machine learning when you're doing something like this, like for xi, yi, and zip of xy, where x is your data, training data, and y is your labels, right? So this is a very, very useful pattern that you'll use all the time. So others that are useful are args and kwargs. So these are useful if you have an arbitrary number of arguments to a function. Like let's say a function takes in, I don't know, it could take in a list, right? But let's say you don't know how many numbers you're going to be adding. So you can just add something like kwargs, and it just like the function will keep working regardless of how many things you add. All right, so we're already about a third of the way through the book, maybe. So let's see. So they talk here about visualizing data. Like, yes, you want to be using matplotlib. There's tons of visualization libraries. Like there's some by default in Jupyter. There's the grammar of graphics libraries like Plot9 that I would highly recommend you learn. I have a separate video about that. Um, and then, like Matplotlib will have all sorts of the basic stuff. It'll have like pyplots. And typically the way it works is that you'll have some data, right? And then you basically set what you want your x ticks to be, your y ticks, your x labels, your y labels, the names of the labels, a title for the plot, and then you say show. So you can sort of think of it like a plot is this object where you pass it in its arguments one by one, as opposed to passing them in a bulk. But I believe you could just pass all of these in a bulk in some form of dictionary. But this is like the more common way to do it. So yeah, I mean, line charts, scatter charts, all sorts of visualization. I'm not going to talk too much about visualizations here. And this was sort of where this book started to get interesting for me. So here with the linear algebra, let's say, so this is here, like let's say doing a vector subtraction or a vector addition. So you'll see here the zip syntax I was talking about earlier. Um, you can do vector sums, you can do scalar multiplies, like the means of a vector. So all of these become like these very, very short code snippets, and they'll make your life a lot easier. Right. So what I was proposing before is that you would say, well, vi times, let's say you'd say something here in vector sum. I propose a version that's slightly more complicated. So here, like, look, the vector add is actually a list, right? Because you still get a new vector after you add vectors. But if you want to do the vector sum, sorry, like let's see here, no, let's do the vector, where is it? The dot product, actually. So in the case of the dot product, what you do is that you're multiplying elements one by one, like in each of these two vectors, you're multiplying them. And then you're going to get a vector, right? And then you want to sum up all the elements of the vector. So an easy way to do this is via like this zip operation makes it really easy. So you basically, because v and w have the same dimensionality as vectors, this becomes like very easy to do. So yeah, so I mean, if you're doing other stuff like sum of squares, then what's nice about this. Like once you have a dot product, you can use it to do sum of squares because it's just a vector dot product to do it itself. You can have a function for the magnitude of a function, and now you can see, well, we're starting to build like the basics of a linear algebra library in Python. In production, though, you wouldn't want to use this because most numerical code is actually written in Fortran. Uh, and so it ends up becoming like much faster, and NumPy and a lot of other numerical libraries will just end up being wrappers that will have a function like this but end up calling a C code via a foreign function interface. So like most languages today let you call C very easily. So if you're like a library maintainer who's really worried about high performance, like it's how you would end up implementing something like this. So if we set that a vector is just a list, right? Like remember, everything in Python can be a dictionary or a list. Then a matrix can be a list of lists, and so those lists of lists will let you determine this. So um, let's say, for example, you want to determine the shape of a matrix. Well, you could say, well, the number of rows is the total number of lists that are in this thing, and the total number of columns is the length of any row. And the idea here is that, well, matrices in general have the same number of columns for all rows, right? So this ends up working out. And so you can build some helper functions here for yourself, like, well, get the ith row, get the jth column, create a matrix. So all of these ideas are built up from these other foundational libraries that we've built. So the next chapter is really about statistics. And so with statistics, there's a couple of stuff you really care about, right? Like let's say the mean and standard deviation. Like if you look at mean here, it's like a one-liner, right? It's the sum and it's the length. And you can imagine that like if you don't have like these implemented in a library, it's not too complicated to implement like length of a list or the sum of a list. But regardless, like these exist, so you should use them. Similarly here, like the median, for example, like what they're doing is that like, well, they're sorting the array, and then they basically take a look at the midpoint. And if the list is odd, that means that there's a strict median, right? Because the list will look like, let's say this is the median, and then here there's four elements, and here there's four elements, right? So this is if the list is odd. But if it's even, then you can't really do this. And so what you end up doing is you basically take the two elements at the midpoint and take their average, and that's how you compute the midpoint. And so for a list with an even number of elements, the median doesn't exist in the list itself. Whereas if it's odd, then it exists in the list itself. And so there's variations of the median, like let's say the quantile, which is like what percentage of the values lie in a certain range. And the way you would do this is like, well, after the list is sorted, you basically you count the total number of elements that exist after the 75th percentile. The mode is basically looking at the values that show up the most. And so what you can do is you can set up like this counter data structure, but like another idea is that you could make various, like you can make a single pass over a list. Every time you see a number in this list, increment a counter in a dictionary, and then spit out the value that's the highest. And so it works by making two passes in this sort of trivial scheme, but you could also, in the same pass, keep track of the dictionary, in which case you can make it work with just one. So I talked about this in the earlier tutorial, but a lot of times when we're doing data preprocessing in machine learning, like machine learning algorithms don't understand what a string is, and like you can't have values be of different ranges, so you want to denormalize them. And the way you do this is that you basically figure out what the mean is, and remove the mean for that feature value for each element, and then you divide that by the standard deviation for that feature. And so this ends up, I don't, it's not here for some reason, but yeah, that's generally how it works. Similarly, if you're doing stuff like the covariance or correlation, all of these can be computed from standard deviations and covariances. So again, you can see how the code is building on top of each other. And this is sort of like an interesting example of a statistical puzzle. I don't think it's very relevant for this book, but it's just an interesting thing to think about. Where if you have two subsets, let's say like men and women, for example, and you have a machine learning classifier that does best on both of those subsets of the data, it's not guaranteed to do better on the aggregate. So very confusing, but it's basically Simpson's paradox, and they discovered this by looking at Berkeley admissions for engineering, I believe, at the time or something. So yeah, it's very important, like thought experiment and just gotcha. So another really important, like here I sort of briefly already talked about conditional probability in the theory section, but if you see this syntax here, like what this means is the probability of E and F happening. If you read something like this is the probability of E happening given that F happened. So that's sort of like how you would think about it. And so the probability that E given that F already happened is the probability that both have happened divided by the probability of F happening. So there's a couple of laws here, and you can sort of implement some of this stuff, and you can see like Bayes' theorem here. And like here, for example, they implement a couple of like distributions. Like for example, there's the uniform PDF, which is 1 if x is greater than 0 and less than and 0 if x is less than 1. So you can see here, like they don't have to be like these clever one-liners all the time, but a lot of times, like at least like I mean, let's take like the ReLU activation function, right? So let's saying like def of ReLU of x. Basically, you would say if x less than 0, then return 0, else return x, right? So this is like one way of implementing a ReLU. So, it sounds very complicated, right? Like rectified exponential linear unit or something. And you can also, I believe, implement this with a one-liner, right? You can say, like it's uh, return x if x greater than 0, else 0, right? So this is how you would implement a ReLU in one line of code. So other like there's famous examples like when you look at the normal distribution, you can plot out all the math for it, right? Like this is just a simple like formula that you apply. The nice benefit of having it in code is that you can then just like put this in Google Colab, for example, try out some different variables for sigma pi, and then use matplotlib to draw this for various values. And this helps you get a good intuition for how this stuff actually works. Whereas with the math, I think it's a bit more involved. Right, so moving on, the central limit theorem. So the central limit theorem really tells you that if for most like processes, if you process enough data for a random variable, in the limit it starts to look like a normal distribution. That said, this is not always true. Like there are power laws in real life, like as in this will be true, for example, if you plot heights. Whereas like it may not be true, let's say if you're plotting income. What's going to happen is that you would have like more people at the tails, like more like lots of poor people, lots of rich people, and you're not going to have all that many like these sort of middle class people don't sort of exist in the same way that they cleanly do for data sets like heights. So other important stuff is like hypothesis testing, which is that like the idea here is like with p-values and stuff like that and confidence intervals. Um, this is sort of interesting, I guess, like just as a way like where you're looking at the uh, like total number of samples that you have and how meaningful they are. And I want to get to, I think this was for me my favorite chapter of this book was the gradient descent one. And so it first off starts by saying, well, like we have like the sum of squares, right? Which is you take a sum, and it's like if you look at the syntax, right, it's like literally the sum of all the squares of all the elements for the elements in a vector, right? And so we're saying we frequently need to minimize such functions. And so how do we minimize such a function? Well, you take the derivative and set it equals to 0. Uh, but there's a couple of other techniques, right? Like one is the difference quotient, where you're taking this is the formula in math textbooks for how to take a derivative of a function. And basically, the idea is that you take a very very small number h, and the smaller h is, the better that your approximation is going to be. And then you see how much your function changes in this small space, and then this gives you a difference quotient. And note that like the difference quotient isn't applied for the function as a whole, right? It's a function of the function, but also the input, and then of the sensitivity of this test. So let's say if you want to take the derivative of sum of squares, then it's really just 2x, right? Um, so yeah, and you can actually plot the difference. Is interesting. So they're actually plotting the difference between the quotient, uh, and then see they take a very small h. So the smaller the h, the better this is going to be. And then what you can do is that you can essentially estimate the gradient by one taking the partial difference coefficient. So let's look at this thing. So this is saying, well, we have a w, the ith partial difference quotient of f at v, right? So this is vj plus h if j is equal to I, else 0. Sure. And then for j, vj in enumerate of v, right? So then this is the, right? So the j is your index, right? It's the your jth, it's basically your jth feature. Vj is the value of your jth feature. And then what you're doing is that, well, you add all of these values in an array, in a list, sorry. And what you do is you basically add this difference, and then if j is equal to I, then you just don't add anything. So the interesting thing about this is that here, like so this is sort of like this is the gradient descent algorithm. So once you get a step size, so your step size is basically going to be uh, like here. So you're going to have like some sort of vi, right? And then you want to change this vi by a step size times a direction that you want to go in, right? And then you get this direction in machine learning from your loss function, right? So this direction, really, you're gonna get it like it's a function of your loss. So it's basically a function of your prediction, as in let's say wx plus p, right? And the actual label. So that's how you would get this prediction, and this is sort of how this fits back to the way libraries like TensorFlow or PyTorch work. Like they sort of do this step for you automatically, right? So here, what we're gonna do is, okay, well, we're saying, well, we're gonna start our value at some random value, and then we're gonna go in a direction of a gradient. So we're just gonna keep taking steps until the difference between two successive steps is very small, in which case end. And so this is really saying like, we converged, and so if our loss looks like this, that means we're good. But if our loss looks like, let's say, like this, and then we just came in like here, for example, which is not the lowest point, it's not, then you could say here that the function was minimized. So let's just double check that we make sure we understand this part here, right? So one is to get the gradient of a vector. You take the gradient you take the sum of squares of the gradient, right? So the sum of squares of the gradient is 2 times vi for vi and v, okay? So this gives us a gradient, and then we take a step of v along that gradient using this step size, right? So this is our step size, and then this is the direction. So the direction we're getting from our gradient, and the gradient we're getting from an estimate here of vi. And so you can do this basically, yeah. So this just always is gonna make sure you get to 0, because minimizing, 2vi means that vi should be equals to 0. But if this is a more interesting loss function that, like, let's say like a complex neural network, for example, then you can end up like minimizing a loss on some problem. So typically, also when you're taking some sort of step like this, you're not going to take it over a single example. And the reason that's the case is GPUs have very poor performance at batch size 1. And so what you generally want to do is you want to batch in a whole bunch of examples and take the gradient with respect to all of those examples at once. Right? So if you're minimizing a batch, then you can imagine here, well, you have your gradient, they're passing in the gradient function. And then here, yeah. So this is interesting in that, like, let's say you want to minimize a function, you would do this. But if you want to maximize a function, well, all you really need to do is negate the function that lets you maximize it. Right? So this is like another nice benefit of using a functional approach, in that you can sort of like, once you build nice modules, you can change them up. However, though, like typically for a lot of data sets, you don't want your algorithm to be influenced by the order in which your data was collected. And so instead of just picking the examples one by one, you will randomly shuffle your example. And thankfully, there's like in the random library this nice function called shuffle. And so what this will do is just basically switch up the indices. So here, like, look, you have so I for I in enumerative data. So you're going to create a bunch of random. So one is you're creating as many indices as there are elements in your data, right? The next thing you're doing is you're shuffling these indices. And then at every point, you're yielding that index of the data set. And so this is just like a good way to like a very simple way to generate like an like a random order of traversal of your data. And so when you want to minimize like a function, let's say so this is your target function that you want to minimize. This is your gradient. This is your input. This is your this is your label. This is your learning rate, and then this is your initial guess, right? So let's put everything together and see how this works. So the first thing is you're going to set up your data set, which is zipping your x and y. You have your first theta and alpha are basically just randomly. So your first theta is basically going to be totally random. And you're going to say, well, I want to have a minimum theta and a minimum value. And at this point, because you don't know what they're supposed to be, you just set that to float infinity. So the largest possible value for a value where you're trying to find the minimum. And then you also keep track of iterations with no improvement. And so this will give you, like, basically think of this metric as patience, as in, like, how long do you want to wait until your metric gets worse to tell yourself, like, okay, I think we're good here. So the first thing is, we can ignore this part for a second. And what you do is, well, you take the sum of the target function. So you take the target function at xi, yi, theta. So this is your basically your predict for xi in data. And if the value that you get is less than the minimum value, then you know that you found a new minimum. And you can say, well, great, it's been, I can reset my patience because I found a new minimum. And it means that this learning rate is good. If you're not improving, then what you can do is that you would multiply your learning rate by 0. 0.9. And because the initial learning rate is 0.01, you're making this learning rate even smaller. So you're going to make it slower. And so you want your steps to be slower while you're going down, as opposed to doing them like this, like where it's ping ponging and you may not be smoothly traversing the space enough. Finally, you in order, like, and you take a random order because this is stochastic gradient descent. You take the gradient of a function. To compute this gradient, you take your xi, yi, and your theta, right? So this is basically, think of this as your loss. And then what you do is you subtract from your parameters. So vector subtract is, just think of this as saying like theta is equal to theta minus alpha times the gradient, right? And so I'm just gonna make it simpler for you. So this is like theta is equal to theta minus uh, alpha, and then uh, here, right? So this is sort of what this formula looks like, but this is what the code looks like. So it always helps. Like, and even in some languages right now, you can actually write up this code by having Unicode characters. So you can just make your math look exactly like your code. So another thing here they start to talk about is using like Python standard N. So it's not something I want to talk too much about, but you can obviously combine like you can combine command line interfaces with Python. I actually pretty much use Python as my scripting language at this point because I'm not like really good at Bash. So you can open files, you can read them, you can set delimiters, you can, parse everything in some sort of dictionary. If you want to parse HTML, there's a really good library called Beautiful Soup. I've used it a couple of times, like one time to parse leaderboards for a Dota competition. Once you parse it, you can have a data set that you can do whatever you want in, and then feed this to some sort of machine learning algorithm. And so here, for example, they're just plotting this. Oftentimes, like when you're making HTML call HTTP calls to some sort of library, it'll give you back JSON. There's libraries where you can easily parse JSON and spit it out to your terminal and do stuff with it. So this is all like very simple stuff that you can do yourself. So for example, they're saying, okay, well, working with data. So we talked about this, like the idea of like, let's say bucketing and plotting histograms. So this is should be familiar to you if you've looked at the visualization chapter. So it's sort of doing similar stuff. So I think we can skip this for now. Yeah, so here it talks about like rescaling and why you want all of your values to be zero, mean, variance one. It's very important because you don't want features that are large to have a disproportionate impact on the on your prediction. You want like the magnitude just not to matter. Right. So here it's like another techniques like looking at directional variance. So this is like with principal component analysis, like looking at looking at the features on which your features change the most. So those are typically the most interesting ones to look at. All right. So now we're at machine learning, right? Um, so yeah. So for example, I really like this when I first saw it, like doing like a train versus test split, for example. So imagine that you don't have a train and test split, right? You just basically created some sort of giant matrix X and Y from some sort of text data set. And what you want to do is you want to split the data. And the way you would split the data is you would have like your results here be two different lists. And what you're doing is for each row in this data set, what you can do is you can flip a coin, and if this flip is less than a certain probability, then you append it to one row versus another. So let's say now this coin was, let's say this is 0.9, then then the results are much more likely to be in one result versus the other. So this lets you create like basically changes in how balanced the data set's supposed to be. So you can basically actually set a percentage for it, right? So this is what the split data does. And then essentially because split, so first off, data is XY. Split data returns two lists, and those are your train and test. But also your each of these is also a split of both your x and y. And so what you can do is instead of zipping, you can unzip them by doing zip and then star train. So this lets you spit out like your x and y respectively. So this makes it really easy for you to just create like a custom data set from some data that you have. So when you're looking at like, well, is this result good? You can look at metrics like true positives, false negatives. So typically, as your algorithm is learning, at every step when you're making a prediction, you want to keep track of your true positive, true negative, true positive, and false positive. And once all of these are updated after the training is done, you can independently compute the results for each of these metrics, and you should have a good time doing this. They also talk about the bias varies trade-offs. It's something I've already talked a lot about, which is essentially complicated models will fit your data better, but they'll generalize worse. So there's always a trade-off with how complicated you want your model to be. And let's see. So this actually code I actually really liked back in the day. So this is an approach for k-nearest neighbor classification. So imagine that you're basically labeling different points, right? Uh, so let's assume that you had k clusters, and each of these k clusters correspond to some label, right, roughly. And so what you want to do is to figure out which like which like let's say given a new point, let's say these are your clusters, right? And these clusters, like they're clusters because they have a whole bunch of points around them. But now you have a new point here, and you want to figure out like, well, how should I classify this point? And so what you're gonna do is that you're gonna basically look at the k, like you're gonna look at like for example, one idea is you could sort your clusters by proximity, and then make each cluster like vote for what they think your label should be. Another way is to just look at your nearest cluster and just take its label. So these are like two different approaches you can take. Right. So okay. So like before we get to deep learning or anything like that, a very popular algorithm for just classifications in general is naive Bayes, and it's called naive Bayes because here, let me show you this. Okay, yeah. So the name naive Bayes really comes because it's really that you're treating all the features as being independent for a certain classifier. That's generally not true. So for example, if you look at this here, well, let's say the probability that this is spam, given that it has the word Viagra in it, and then given that it has the word Nigeria in it, and then, given that it has the word Bitcoin in it, for example. So those could be three possible features, right? So you could have each feature is some code that you would run on this text that would compute them. And so then if you're trying to figure out the probability of this is actually being spam, you can look at the baseline probability, like roughly how many of your emails are actually spam, right? Divided by the probability of these words existing. Multiply this by the probability that the existing features you have that the existing features exist, given that the data set is spam. So this is using like Bayes' law for essentially classification. And this is why this is called naive Bayes, because they just assume that all the features are independent. I haven't used naive Bayes like ever, I can say, but you can sort of see here how it works, right? So you have a classifier, and then this init function has like a I guess what's k? Not sure what k is. Yeah, I don't care too much about naive Bayes. Yeah, linear regression, interesting. So with linear regression, for example, we said that you're essentially predicting a real value. That's what prediction is. You're predicting a target. And so your prediction, again, like your model is going to be like some sort of like beta xi plus alpha, right? So your parameters are beta and alpha, and this is what you're trying to learn. And the error on your prediction is basically the difference between the actual label versus what your prediction is. And then, but instead of just looking at the error like this, like you can take the sum squared of all the errors of all of the data set, and this gives you like a better measure of your error. The nice thing about linear regression is that you can fit it via gradient descent, but it also has a closed form solution, which means that closed form is always good because it means that you can compute the value almost instantly. And what the optimal values for it are is you'll take the correlation of x and y times standard deviation of y divided by the standard deviation of x. And then your alpha is basically the mean y minus beta times mean of x. We can work through the proof maybe some other time, but just what's important to know is that generally if you have a closed form solution, that makes your life very easy. It means you can implement this very fast. However, almost no problems in the real world have closed form solutions, so that's not something you really need to worry about, and it is why people end up using gradient descent. Yeah, so here they talk about how to do this with gradient descent instead. Is like, let's say you have this error, right? This is the error, but then the gradient of the error is basically going to be is going to be the derivative of the loss, right? So let's take a look at this. So what you want to return is minus 2, right? So this is basically this error is squared. Instead, what you want to return is 2 times the error of alpha, beta, x, y, y, I for your, this is for the, yeah, so this notation is confusing. So this is your bias, this is your weight, and I guess like it's confusing because your bias is A instead of B. However, like this is sort of how to think about it, is that like, well, you have this function, right? And you want to take the derivative of this function with respect to your parameters. Your parameters are alpha and beta respectively. And then your error is actually if you look at the error, it looks like this, right? So it's yi minus predict. So if you write the whole thing out, it's going to be yi minus beta times xi plus alpha, right? And so when you're taking the derivative of this thing with respect to xy, for example, with respect to beta, you're going to have an xy parameter show up. But if you're taking this derivative with respect to alpha, then xy becomes a constant, and so it cancels out in the derivative. So here, okay, multiple regression. So generally, like what I want you to think about here is that, well, let's say you're predicting a couple of things at once, right? So there's two ways of doing it. So one way is having like each of these predictions be completely separate for each problem. And another way is to say, well, I want to have a beta, sorry, I want to do a predict, let's say for like this, like there's going to be a bunch of predicts, predict plus predict. And then you give them each a weight, right? So like say this is W1 and then this is W2 and W3. So this is like you would hard code these weights, and this is sort of a way to balance out what's important in a multi like in a multi-label problem, um, or just like generally like a multiple regression problem. Uh, or you could learn them from data, but that's like a bit more involved here. Typically, these would just be hard coded. Or like a simpler way is to just treat these as different problems and just have a separate predict for each subset of these problems, and not worry about how this works. All right. So another important thing to think about is like regularization. Sorry. So with regularization, you're essentially adding a penalty on the magnitude of your beta and alpha, right? So let's say you have this loss, and then you have this penalty. And so the penalty, like the gradient of the penalty here, like let's see how they compute it. So the ridge penalty is alpha times the dot product between beta and beta itself. So this is gonna be basically like I believe this is just L2 loss, right? Because this is essentially looking at like this is saying this, like you have beta squared, right? And so the gradient of this thing with respect to itself really is here. So it's you're essentially going to have, because it's beta squared, like alpha beta squared, then the actual function is going to be 2 alpha beta, right? And then because you have a whole bunch of these betas, you would basically like this is what the zero here is doing, is essentially just making sure that you have a starting point so that you can accumulate all of the gradients into the same list. And if you wanted this to be L1 loss, then you could just say here instead have like absolute, and then compute the derivatives yourself. So hey everyone in chat, by the way, if you have any questions, like feel free to ask me. This is supposed to be an educational stream. So logistic regression, I've talked about this already. I think this is a terrible name. I would call this logistic classification because it's just a way of turning a logistic regression into a classification problem. So trying to predict like cat, not cat. And the main difference is you essentially have logistic regression, sorry, like linear regression, uh, plus a softmax, which lets you do a classification. So I'm just going to describe now what a softmax is. So let's say here we're going down. So what a logistic function essentially is our problem is how do we turn our model that spits out real numbers and get a classification out of it. So we want a way of turning arbitrary values that can go from minus infinity to values that can go from 0 to 1. So this is what the logistic function does, and this is the equation for it. So you'll notice it has a few nice properties, like it's smooth, it's differentiable everywhere, and it also has a very nice convenient derivative that you can compute. Its derivative is actually logistic of x times 1 minus logistic of x. So this means it's very fast to compute the derivative and it's efficient. And once we have these values between 0 and 1, what we'll essentially do is our model is going to make an output. And if let's say the output is above a certain threshold, like let's say 0.5, then we'll predict a class 1. And if it's below that threshold, then we'll predict a class 0. Right, so here you can see, as I suspected, like there's like the logistic prime here. And so how do you actually compute the loss of this thing? Well, let's assume that the actual class that you need to compute is of class 1. Then the way you compute the loss is you basically take the log of the logistic of the dot of xy beta. So let's just flesh this thing out a bit. So we said that your model is going to be essentially xi beta, right? So logistic of xi beta is 1 over 1 to the e of xi beta. right? So now we're here. So why are we taking this log then? Well, essentially logs, we're going to end up multiplying, like, okay, so let's say you have a whole bunch of examples in your data set, like x1, 2, xn, and then you have y1 to yn. So there's a whole bunch of them. So what we need to do is we need to figure out, like, what's the likelihood that the data was generated using some assumption of what we think the parameters are. So this is sort of like a Bayesian way of approaching the problem, as in, like, you think of your data as a you think of your data as the parameter, and your W as something that you fix, and like your model weights, and then you ask yourself, how likely is it that I would have seen this data? And if it's not likely that you would have seen this data using those weights, that means that your model is wrong, that you should change it via gradient descent. And so we're going to compute basically like a likelihood for each one of these, like likelihood of 1, likelihood of 2, likelihood of 3, etc. And when we're trying to find the total likelihood of this thing, essentially what we're going to do is we're going to take the product of all of them. But the issue is that because these are probabilities, all of these values are going to be between 0 and 1. And what ends up happening is, if you multiply a lot of values that are between 0 and 1, then you end up with something really, 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 really tiny. And the issue here is that this is fine if you're doing this on a piece of paper, but on computers you end up with an issue called integer underflow, where your computer just doesn't have enough bits to represent this number. And so the way we solve this problem is we take the log of this value, and the only reason the log is there is basically to deal with this underflow problem. It's not like forced by the math; it's really like the computers demand it. So this is basically your loss if your prediction is if the actual label is 1, but if the actual label is 0, then you basically take then your prediction then your loss is basically 1 minus what you predicted, right? And so here, let's see how they make this work. And so when they're actually trying to look at the logistic log likelihood of a full data set, now you take a sum, right? Because logs is just a function that lets you turn products into sums. That's why we use logs. So this log likelihood function on the entire data set becomes like a one-liner on top of a function on top. It gives you likelihood for a single example. And then if you're trying to find the logistic partial, so the partial derivative, here what it's going to be is you're going to have like yi minus logistic of this. So this is like your model prediction times what your prediction is, right? And so you can get this if you actually go back to the formulation of the problem here. So let's say you're taking the derivative here with respect to beta, right? So notice how we conveniently left out the bias so that the math is easier. But essentially, you're going to look at the difference between what you predicted on this example with those weights times the label, and then you're going to multiply this by the actual value of that feature for that label. So this gives you a gradient per feature per example, right? So then you want a gradient per example, and the way you do this is you sum up all the gradients for for all the features for a given example. So this is what the sum is. And then you want to take all the sums for all of the gradients, for all the features, for all the examples, and this is where this comes in. Right, so we're slowly building it up. So this is all examples, all features. For example, this is one feature, for example. All right, and so ultimately then when you're like trying to figure out, you notice here, like when we're making this prediction, for each prediction in the test set, we're going to keep track of all of our true positives and true negatives, and then we keep track of our precision and recall, and then we just print those to the screen. And then this gives us a good idea of like how well our model is doing, so we can just chart these as the model is going along. So this was more like the logistic regression approach, and it's actually pretty close to the deep learning approach. But like another tree of algorithms is decision trees. And so I talked about this. So let's say this is like guess the animal, for example. Like, does it have more than 5 legs? Yes. Does it hide under your bed? Yes. Does it star in Charlotte's bed? Web? Yes. Then it's a spider. So the way you would come up with these rules is basically an algorithm like so you can come up with these rules with any sort of algorithm. So there's like auto rule generators that you can use. And then the way you would figure out how to set up this tree is via an algorithm called ID3, which would look at which rules split your data the most. And so the way we split the data the most is, we have this notion of entropy. So this is plotting p minus log p. So that's entropy. So you can see here, for example, like that's all this is. And it just gives you like class probability. So if you're trying to compute the entropy of a partition, so in decision trees, typically you would partition the space into two, but let's say you can partition it into more. Then you can take the partition of each subset, right? And then weigh each subset. So I don't think they do this here necessarily. I don't see it. Build tree ID3. Okay, build tree ID3. Let me just slowly remember how this stuff works. So first off, I just want to quickly show you this thing. So it's used to generate a decision tree from a data set, and it's the precursor to the C45 algorithm, and it's used a lot. Okay, sure. So, okay, they're showing pseudocode, and they're saying, well, you created a root node for the tree. If all the examples are positive, then return the single node tree. If all they're all negative, otherwise, okay, empty. This is not a very good actually explanation. I had a better one. I think there was a better one in the 100-page ML book actually. Yeah, so I do explain this in my earlier video from today, like the 100-page ML book. So I would recommend you refer to that instead for a better explanation because I cover it in a bit more detail. Um, but yeah, and so then other stuff they talk about is like, let's say, random forest, which is essentially a way of aggregating data. So there's a family of technique called bagging, sorry, aggregating models. So if you have a couple of models, they each make their own classification. You count the number of votes for each classification, and you vote for the most common one, right? So then another way, like another more complicated approach is essentially called boosting. And what gradient decision tree boosting is you have one classifier classify on a couple of examples. You keep track of all of the ones where it failed, and then the ones where it failed, you train a new algorithm to just classify those. And so the idea is progressively you would make those algorithms focus on the harder and harder problems. Um, yeah, so you see here, like let's say classifying. Let's do this. Let's say you want to classify a node with respect to a certain tree. You can look subtree, classify subtree. Yeah, so for each subtree, basically, you recursively classify the point. So I guess like while not leaf, say classify subtree input, and then you have some sort of base case that tells you if you get a leaf node, then return what that leaf node is. So then here they're saying, well, like the leaf nodes, I guess either are classes or they're true or false if it's binary classification. So yeah, so here for example, it's binary classification because like is this person junior or senior? I guess is what they're doing. All right. So how do they build the ID tree? So we have some split candidates, and then the split candidates are based on the key on the input, and then okay, there's numbers of trues, numbers of false. If number of trues is equal to zero, return false. Okay, so this is sort of like the base case, right, of the construction. If uh, okay, so if there's no split candidates left, return the majority. That's fine. Otherwise, split on the best attribute. So the best attribute is essentially you take like here. So what this means, by the way, is you're trying to find the minimum of the split candidate, where minimum is defined as this function, right? So it doesn't like minimum It doesn't just have to be the minimum value. It can be the minimum function applied to this thing. Another way to do it would be uh, for like basically four split candidates in uh, so no, sorry, why split candidates mentioned? Yeah, so basically for the split candidates in this partition on those inputs, keep track of them in, and you can do this with a for loop instead of doing this like this. But essentially, okay, well, so you get these partitions, and then you apply this partition by function for each input and each attribute. And then you get some new candidates, and then you recursively build a subtree. So notice here how the subtree is basically built via a dictionary, right? So this is a dictionary, and we're saying, well, we want this subtree to be this value, and then we want the value to actually be the tree construction here. Yeah, this is interesting. Actually, I didn't ever consider that you could build decision trees this simply. I haven't looked at this code before. All right, so example here, let's say they're saying, well, you can partition by, so partition entropy by partition. So this uses partition by inputs and attribute. And then you just return partition entropy of partition values. Okay, so where's partition entropy? So find the entropy from this partition of data into two subsets, right? So one, you keep track of the sums. So how many elements are in each sum, right? And then you take the entropy of each subset of the data and you weigh it by the length of that subset. And then you divide it by the total count, and you do this for all the subsets. And then you return the total entropy for your current data set, right? So going back up, I think this is all good. And so if we can do this partition by, here, where is it? Then this is like a way of computing this entropy here. So I think this is one of the last chapters, but with neural networks, typically here, like you can see, like a logistic regression is just a single like a single layer neural network, right? So it looks identical. You know, it's like the weights and x, and then there's the bias. But then there's also nonlinearity. So deep neural networks are essentially like linear functions. Basic matrices are linear functions with a nonlinearity, and so this nonlinearity is a step function. So what does this thing look like, right? If you were to plot it out, then this thing is going to be equal to 1 if x is greater than 0, otherwise it's equal to 0. So, but this is, you see, this is not very smooth, and so this is why often we end up doing something like a softmax. And so you can see this is like another motivation behind picking the softmax function. So yeah, so here they talk about like the sigmoid function. We talked about this function before. Your neuron output is really just going to be this, right? And so then notice, for example, that at every step of a neural network, you have some input, and then you basically have an output which goes over each layer and then uses that layer to compute the next layer. And then there's a nonlinearity somewhere, but it looks like it's missing here. But generally, this is how you would make it work. And so the way like the way the backprop algorithm works is essentially you have like you can think of this as here. So let's say like you have these layers, and so your question. So at this final layer, you know that you need to change these weights such that you match your output yi. So again, you do this by setting derivatives equals to 0 and changing it in that direction. But you know, what about this, right? Like, well, turns out also, well, you want to look at the changes here. How do they affect, like, basically, if you change here, how would you change this? Like, of the weights? The layer is what's at least 2D. So views inputs as arrays with at least 2 dimensions. Oh, I see. Okay. All right. I don't think this is terribly important. I don't know why they have it here. I think we can look at the core idea here. right? So they're saying here they take the dot, like they're saying they take the dot product of the weights, apply the activation functions, right? So this is the forward prop part. After you do the forward prop, you get the error. And then for the error, you multiply this by the activation prime, right? So activation, okay, it's not implemented here either. Oh, I see, I see. This is like the activation prime is the derivative of the activation function. Okay, sure, sure. So here, in case like you're using, yeah, so sigmoid prime, and then I guess, yeah, yeah, sure. And then tan h also has a nice, oh, wow, I didn't know the derivative for tan h was so nice. It was just like 1 minus x squared. It's kind of cool. Okay, I did not know that. I just learned something. All right, so let's see, going here. Where was it? Okay, great. So we have this delta, right? And so we have a bunch of these deltas. So we need to begin at the second to last layer. Okay, great. So we have all the deltas. So now we reverse the deltas. And then for each I in the weights, we take the layers and we take the deltas and we dot product the layer and the delta and then add the learning rate. Oh, I see. That's it. Oh, I see. I see. Okay, okay, okay. Got it, got it, got it. And so here, really, they're just taking like like for each set of weights, they're finding the activation here. But where does it make it clear that the loss is dependent, uh, that the gradient needs to depend on the layer that comes after you? So let's see here. So delta. So the way it works, like the iteration is for L in range of length of A minus 2. And then it starts, and then it goes down by 1 each time. Right, so let's see. So self of activation prime, self weights of 1t, deltas of minus 1. Okay, sure. Oh, I see, I see. Okay, yeah, this is it, this is it. Okay, easy, easy. So this was it. So you basically, for the deltas, you apply the delta that came before you, and then you multiply that by your current weight times the times the activation function at the current layer that you're at, right? So basically, the output of the forward prop uh, times your weight times the activation at the previous layer. Actually, sorry, the loss at the previous layer. Oh, I see, I see. Yeah, yeah, yeah. Because you're just adjusting to the loss of. Okay, okay, sure, sure. This makes sense. I'll say this is the best one. Then I'm gonna bookmark this. All right, and I think we're almost done with the book. So let's see here. So I actually also really like this code here. So this is the k-means code. So k-means is basically an algorithm to find clusters. So initially, you don't have any clusters. And what you essentially do is you basically try to find the cluster that you're closest to by saying, well, I want to have the min of all the k's such that the thing that I'm minimizing is the squared distance between my input and self dot means of I. Self dot, yeah, actually like the clusters, right? So find the minimum cluster and squared distance. The way you train this is you basically pick some random points and have some random assignments. And then you keep iterating and then you classify each point. If there's no new assignments, you're done. Otherwise, uh, add like you compute the new means based on the new assignments. And the way you do this is basically make sure I point is not empty, so don't divide by 0. So basically, for each for all of the points assigned to a cluster, you look at them and then you take their mean together. Let's see. So choosing k, plotting the sum of squared errors, and looking at where the graph bends. Yeah, so interesting. Yeah, so this is what I talked about. Like you want to just like slowly increase the clusters and see where you get like very diminishing returns, and it's sort of like by eyeballing it, you can feel like it's really here. Okay, hierarchical clustering. We can talk about some other time. So NLP here, like really, what they talk a lot about is like building stuff like n-gram models, uh, like basically like counting all the times some occurrences appear. So also easy to do in Python. Network analysis is like, let's say, looking at like a graph. I don't think it's like a very ML-ish chapter, but it's useful just to look at how you can do dictionaries in Python. Okay, page rank, recommender systems. Okay, item-based, user-based, collaborative filtering. This is all cool. Generally, the main thing I want you to think about here is that, like, if you want to figure out what to recommend, you can do it in two ways. So one is look at users that are similar to you. So you can essentially featureize people and then take dot products between them and then recommend stuff that people like that people have seen. And then if and the other way is to do it based on like the items that you liked. And let's see, so this is user-based suggestions. Yeah, item-based collaborative filtering. So you essentially build like an interest matrix, and then you can use this matrix, and then you can do like some machine learning on this matrix. We can talk about this some other time. Databases and SQL, obviously, like most data isn't doesn't come in a big fat table. So you need some basic SQL to set up like tables for yourself and columns. If you don't know how to work with SQL, you can always build some wrappers on top of it, but this will make your life easier. It's better just to learn SQL. This is a cool operation, I guess, is the group by. It's sort of like a pivot table in Excel, which is, I think, the best feature about Excel. Right, NoSQL, MapReduce. So MapReduce is really just this paradigm of applying a function to different subsets of a data set, and then reducing it means aggregating this information. And I think we're good to go. Like he finishes off by saying like, you could use something like IPython for notebooks. It's very practical. I use like Google Colab quite a bit and Visual Studio Code, but you can, decide for yourself what your environment is. And, he then mentions like a couple of libraries that he thinks are really good. And that's pretty much it. Like I hope you guys, yeah, so I think that's pretty much it. I hope you guys enjoyed this tutorial. Like we sort of covered everything from the data science from scratch book. So hopefully you can use this to review like like your knowledge about machine learning, or if you're learning machine learning from scratch. I think this is a great reference, this and the 100-page ML book. So yeah, I mean, if you enjoyed this, please subscribe. But lets me know that this content was useful to you.